I'm going to try to just remind us a little bit of where we were, and we got a little bit of a refresher earlier when David was talking a bit about contrastive learning. So if you remember, that's exactly where we kind of left things off yesterday. So I was describing this sort of overall approach of trying to create a space, to learn a space where images that we determine to be similar should be close together in that space, and things that are dissimilar should be far apart, right? And then we covered this sort of early work in this space and a more recent approach, right, where we were talking about the idea of considering contrastive learning approaches as analogous in some sense to dictionary learning approaches. And so we're just going to wrap up this before moving on to the last self-supervised learning technique that I wanted to cover, right? So this is another, I think, interesting approach to contrastive learning. And this is work by Chen et al. And the authors build this as a simple approach for contrastive learning, and indeed I think it is simple but effective. And so I'll just talk you very briefly through the procedure. So first you start off by sampling a mini batch. This is what we've been talking about quite a bit yesterday. That you have some large unlabeled training set, and then you're sampling from them in these sort of mini batches, right, through time as you're training your model. And these mini batches, by the way, the size of them, because I was speaking a fair bit about the restrictions on the size of the mini batches. So I'll just mention that, because you're probably familiar with the fact that when you're doing learning either supervised or unsupervised, you don't necessarily have to use batches, right? You could potentially use all of your training data at once. That tends to be limited for different reasons. Number one, for computational reasons, that if you have a data set that's, for example, 1 billion images, it's kind of hard to do that simply computationally in terms of the compute and the memory size that you might have and the storage size. And then also there are limitations just in terms of the algorithms that we use to train, right? So you might find that even if you can increase the size, the number of images you're using, or the number of signals, just generally signal samples, that it actually doesn't train well, right, with the types of algorithms we use, like things like gradient descent. So that's why we tend to use batches rather than the entire set that we have. And so in this case, we are indeed using some batch of samples. And as I was mentioning yesterday, we're going to generate for each sample some augmented version of them, right? So this can be, as we were describing yesterday, maybe some random crop of the image, or you can think of some other augmentation you might want to do. There are many ways to augment an image. Actually, I think I have an example. So here, this is just to give you a flavor of the variety of augmentations that are used, right? In fact, these are some augmentations that were used for this work. And so you can see in the sort of panel A, that's like an image, right, of this dog. And all the other examples you're seeing are different quote-unquote augmentations of that image, right? So there are things like cropping and resizing it, cropping the image and then flipping it, distorting the color, maybe making it grayscale, shifting the color spectrum, putting sort of masked regions, etc. There are many different things you can do and many combinations of these things, right? So you can really get just from one image a wide variety of augmented images, which nonetheless we expect to be similar and close to each other in this space that we're learning. Right, so with that being said, you have your set of examples. You generate some augmented versions of one sample, for example. So you see that here. You have X, and then you have 2 augmented versions of them. You project them into some space, right, using this function g of x. And that projects your 2 samples into the space that you're learning, right? And then so what you want to do is that you want to maximize the agreement. As David mentioned earlier, you want these representations to be close in this space, right? To ideally almost be the same, right? And that's because what we have determined is that if this is the same image with not that much change, and what constitutes that much change is sort of left for us as experts, then they ought to be close together, right? Because the semantics of the image should not have changed. And so this work does exactly this. And then the loss that is trained is what you see there. It's some sort of like normalized cross-entropy loss. And this is quite simple, as I think you would agree, but quite effective. And so this is going to be the last work I'll talk about from the contrasting learning framework. But yeah, before that. Yeah, good question. So why would you want to do a dot product? So a cosine similarity. So the cosine similarity is going to be bounded, right? So you're going to have, so that's going to give you sort of, let's say, calibrated distances, right? So you're going to have a distance that's bounded, and therefore it's going to be sort of easier to make comparisons. And then why do you have this normalization? I guess you could say for similar reasons, right? So this way you can think of it as a probability, right? So you want to kind of say this normalization, a probabilistic normalization, is going to say that if I have I would expect the kind of likelihood of these two to match, right? This I and this j to be matched to be high, right? And you want to make this as high as possible. You want to make this a peaky sort of distribution, right? So it's really just ways of normalizing the data, which makes all of the optimization more tractable. Okay, so this last work is I think a kind of interesting twist on the idea of contrastive learning. So we've been speaking so far, I think, pretty exclusively about contrasting different images, right? Augmented views of images. So this one instead takes a kind of different approach. And instead, it's proposing to compare cluster assignments, right? So what it does essentially is it creates a set of clusters, and it does this in an online manner, but it's not super important. So you create a set of clusters, and for each cluster, you generate some prototype for that cluster, right? So some sort of representation of that cluster. So an obvious example would be taking all the samples in the cluster and computing the mean of that cluster. And that gives you a representative of the cluster. Okay, so first it does that. I think I have So it computes these prototypes, right? And then what you do is you have a sample. So you have the sample X. As always, you generate different views of it, right? Once you have your view, you run it through your representation that you're learning, your f theta, f parameterized by theta. This gives you a representation z. And then you generate a code, which you can think of as a probability distribution over the prototypes that you have, right? So it's basically going to give you some probability of that sample, that view of that sample, z, belonging to each of the potential clusters, okay? And that might be a very peaky distribution. It might be something else. Maybe it's sort of like equally distant each. Hopefully not if you know. Depends on the data, right? But this could be a distribution of an arbitrary shape, right? And so once you have that, you also have the second view, right? And so you have this second view that you also generate a representation of, okay? And then what you're going to do is you're going to take this loss that's going to make a comparison between the probability distribution that you generated with one view and the probability distribution that you generated with the other view. And essentially what you want to say is that the probability of this sample belonging to each potential cluster should be the same even if the views have changed slightly, right? So it's a kind of a twist on the idea that the view should have the same sort of semantic representation, right? It's basically saying that if this view has this probability of belonging to cluster I, then it should be the same for the other view. Right, and this is basically kind of what I just said there. So you take a view Z, you take a view Z from view T, you take a representation Z from view T, you take a code from view S, and then you compare them, right? So you compare them and you say that they should be sort of matching the probabilities that they generate. Okay, so that concludes contrastive learning. And if just to cast your mind back, we covered some kind of ad hoc pretext tasks earlier, right? So things like rotating images, solving jigsaw puzzles, solving sort of sequences that have been shuffled. Then we covered, contrastive learning. And then now we're going to look at just a couple examples of a different flavor, which you can call self-distillation. So why the motivation for this? So we were discussing the fact that contrastive learning methods work pretty well. But they are a bit finicky, right? So you kind of have to make sure that your positives are chosen well. So you have to think very carefully about them. And what that means in practice is you have to think of things like what sort of augmentations make sense, right? What kind of augmentations would I do that would make the images reasonably similar? I need like a diverse set of augmentations, for example. And then also you need to choose quite a lot of negatives, right? A lot of the value of the contrastive learning comes from indeed the contrast, right? So you have to generate a lot of contrastive examples in order to have the model be really robust. And so that's not trivial, and there's a lot of work goes into doing that well, and a lot of papers get generated on trying to do that well. So other works have considered trying to find alternatives to this, and one of them is in sort of this self-distillation framework. And so I'm just going to take you through this relatively slowly, just to make sure we're all on the same page. So how many folks are familiar with the concept of distillation, model distillation? Okay, so let me go through it a little bit. So just like at a super high level, model distillation was a method that was proposed probably many times, but at least I think most famously recently, let's say, to distill, as the name suggests, distill the sort of the information encoded from one representation, one network to another. So you tend to have these two networks. One is called like a student, one's a teacher. And the student is basically learning to generate the same output as the teacher, right? So the loss tends to be this: you have an input, you throw it into the teacher, you get some output, typically a probability distribution. You throw the same input into the student, and then you want what the student generates to match what the teacher generates. Okay, that's just the basic concept of distillation. Why would you want to do that? You know, if you already have a teacher, why do you need a student? Typically, it's I would say the main motivation is for learning students that are more compact. So you have a teacher that might be quite a big model, then you have a student model that's smaller, and so you're going to be able to generate the same output with a smaller model. And there might be reasons why you can train a model that's bigger and then transfer that knowledge to a smaller model as opposed to just training the smaller model from the get-go, right? So that's kind of the motivation of distillation. And so this work takes that idea and then it kind of applies it to this sort of self-supervised learning case. And so the way it does that is it has these two networks. So one is indeed considered to be a teacher and one's a student. So the way you start off is you have these two networks and you initialize them randomly. So they're going to give you, they haven't really learned anything, but they haven't learned anything at all. They're just randomly initialized networks. And so if you take an image, as always, you apply a pair of transformations, giving you two different views, right? View t prime. You run them through the network, one through the student, one through the teacher. What you want to enforce is that the output of the student is the same as the output of the teacher, okay? So in that sense, it's a distillation approach. And so this might sound a bit weird. Why would we do this at all? So just to start from scratch here. So what this is doing, it's saying that even if these are basically random spaces, we do think that because the views are views of the same image, we want them to match, right? So we want the student to match whatever the representation is of the teacher. And the reason we want that is because we consider them to be semantically the same, so we want them to be close to each other. We want the student to sort of match the output of the teacher. And this simple approach of training the student to match the output of the teacher results in a student network that performs better than it was performing randomly, okay? So it's not performing very well, as you would imagine, but it is performing better than training randomly, than the random network, I should say, the random initialization. And so what you can do is you can sort of bootstrap your learning on this process. Now you have a student that's a bit better than it was before because it was trained to match the teacher. And then what you do is you update the teacher, and then you update the student again. So you go through this iterative loop of updating the student based on the teacher and then updating the teacher. And you update the teacher in a slower way. And so this is the concept of what they call here bootstrapping your own latent. And this is quite, maybe not the most intuitive approach, but performs quite well. So I'll talk a little bit about another method that's quite similar. And I think maybe we'll give a bit more intuition. Yep.
I didn't get about the updating the teacher.
Yeah, let me talk about it right now because it'll be clearer here. Yeah, good question. So, okay, let's talk a little bit about the teacher, right? So the teacher is updated this way, right? So you have the parameters for the teacher, so that's theta t, and you have the parameters for the student, so that's theta s. And so theta t is updated as you see there, right? So it's some linear combination of the current version of the teacher and the updated version of the student, right? So another way to write this is kind of like theta t plus 1 is equal to lambda theta t plus 1 minus lambda theta s1 plus 1, okay? So you update the student, so you have theta s plus 1, and then you use that to update the teacher, right? The key thing here is that lambda is a really high value compared to 1 minus lambda, right? So lambda and 1 minus lambda sum to 1, right? So it's a linear combination. But lambda is much bigger than 1 minus lambda. Like typically people have lambda, use like a lambda equal to 0.99. So basically you're saying that your update is going to be 0.99, the current model, and 0.01, the new model, right? So that means that your teacher is varying very slowly, okay? So that means it's like pretty stable. And so that is why, and in that case, for example, the teacher is not being updated with any, it's not being updated, so you could say via backpropagation, right? It's just an average, and it's called an exponentially moving average because the difference between lambda and 1 minus lambda is sort of exponentially, one is like an exponential factor of the other. Is that clear? Okay. So in this case, this is another example of self-distillation, right? It's very similar to what I just described before. You have your input, you create two views, you run them through a teacher network and a student network, you apply a softmax to your outputs, right? So you get probability distributions, and then you ensure that they match. You use a cross-entropy loss and ensure that these probability distributions are matching, okay? And so you notice there that there's no concept of negatives, right? They're simply saying that you want the student network to match the output of the teacher, where the teacher is slowly varying. Right? And this is kind of just basically saying what I said, right? So this is just a cross-entropy loss between the student output and the teacher output for all the samples that you're looking at. And I mean, I won't go into the numbers, but this is basically just to show that this method works quite well, right? And so there's an argument to be made. A lot of this is very empirical, right? So a lot of things depend on, it's hard to make, I think, really robust comparisons between methods, but it is, I think, certainly shows that it's at least as good as, right? It's a very good alternative to the kind of contrastive learning approaches we've been seeing before, where you have to really think carefully about choosing negative examples. In this case, there's no concept of negative examples. It's simply, at least not explicitly, right? But basically, you're simply saying that I have different views, and I want the different views to, when put through two different networks, I want them to have the same representation. And that in and of itself gives you a rich notion of similarity. Okay, so that closes the chapter on contrastive learning and distillation. And so now this is going to be the last type of self-supervised learning approach that we'll talk about in this session. So this is the general area of denoising autoencoders, and this is a very broad topic. I'm certainly not going to cover it in any real detail. I'm just going to give you basically flavors of how this is used for training visual representations, and I will note that it's used for training all kinds of representations, right? So not just vision, certainly, also language, audio, text, many things. So I would say it's pretty intuitive, right? So let's imagine, so maybe I should start off with autoencoders, actually. So an autoencoder, I'll just kind of illustrate it here using this example. Let's say you have a signal. Let's say so you have the signal x, okay? Let's imagine that you learn some function f parameterized by theta. Forget the x tilde for now, right? So let's imagine you have x and you have some function f theta, and you learn this function such that it maps it into a low-dimensional representation, let's say y, okay? And then you're going to learn another function, g, parameterized by theta prime, that's going to map it back into, it's going to map it into another representation. And what autoencoding, what you want to learn is to reconstruct the original image, right? So typically with autoencoders, you have your signal x, you project it into the space so that it gives you this output y, and then you reproject it into another space that should be the same, should reconstruct your original image, okay? So that's the original signal, just more generally. So that's the concept of autoencoding, right? So you're encoding kind of yourself and learning to reconstruct, right, your original signal. And so what a denoising autoencoder is doing, as it probably becomes a bit clearer now, is it's going to be able to reconstruct a signal that has been, where some noise has been introduced. So it's going to denoise while it's autoencoding, okay? And so the process is what you see here. So you have your input x. you corrupt it somehow, right, with some sort of, in some stochastic way. So in this case, you just show an example of maybe just disrupting these two elements in your vector. Once you have this corrupted signal x, you're going to learn this function f parameterized by theta, and that's going to project it such that you get this output signal y. And this is typically a lower dimensional space. Very often this is used for dimensionality reduction purposes. And then you're going to reconstruct it. So you're going to generate from y another representation, z, using this function g. And then you're going to compare your z to your original input. Right? You're not comparing it to your corrupted input. You're comparing it to the original input. And you want the comparison, you want the distance between the two, the difference, to be low. I.e., you want to reconstruct your original uncorrupted image, right? So this is quite key. The input is x, the input to f is x tilde, corrupted, but the comparison is with the original, right? So you're going to taking something that's corrupted and reconstruct the original image. And this is done, for example, in this work by Vincent I think, et al., uses a squared error loss, right? So the losses don't have to be very complex, as you probably noticed. And this was work from 2010, so a few years ago now, and even then, there was quite a lot of potential, right? So it showed a lot of potential for this work, and you'll see how these types of approaches have been used quite effectively since then. Yeah, one other point I think is interesting to note here is that in this work, they also gave an interesting, I think, interpretation of what you're actually doing here, right? So what does it mean to do this denoising, right? So a kind of geometric interpretation is illustrated here, taken from the paper. So let's say that you have your data, x, and let's say that it's on some manifold, right? And that tends to be the assumption when you're doing dimensionality reduction, because you're basically saying, I have this feature that has some dimensionality, maybe it's a 1,000-dimensional vector, but the signal itself can be represented with, in a more compact form, right? So, for example, you might say, okay, I have something that's 1,000-dimensional, but I think actually the underlying structure can be represented maybe in 10 parameters or something, okay? So that's the concept of having this low-dimensional manifold. And in this case, the interpretation is that, let's imagine you have this manifold that's represented by the line. So you have all the points in your space can be sort of falling somewhere in this manifold. And you can think of the process of introducing noise as sort of pushing your points potentially off the manifold, right, into some space that makes it quite far. And then so what denoising this autoencoding does is it sort of pushes it and projects it. It learns a projection such that it sort of pushes it back onto the manifold. Let me just make sure I didn't skip anything. Okay, so that's the general concept of autoencoders, and basically I'm just going to run through a few ways in which this has been used recently in some recent methods. So the first one here is work by Partak et al. And this, I don't think we've seen this quite before. We've seen some examples of masking, but in general we haven't tried to reconstruct it, right? So this one is an example of what the authors call in-painting masked regions, but it really is a kind of, it's really a reconstruction problem. And so the key idea here is that you're going to corrupt your signal by introducing a mask. So you can think of a mask in this case as a corruption. You're going to input this corrupted signal into an encoder. It's going to give you some low-dimensional representation. Then you're going to use another model, which we call a decoder, which is going to give you some reconstruction, right? And you see the reconstruction there. That's what you want to learn to do. And so, yeah, as I mentioned, you can think of this as a masked denoising problem. And so this is the loss function that's used, and it's quite simple, so I'll walk you through it. So you can think of a mask, so M hat is this mask. It's a binary mask, just has zeros and ones. It has ones where you don't want to mask. Let me just see, is it one where you don't want to mask? So the ones, Yeah, so this, all right, so this is, yeah, so you're going to have ones where you're masking, and you're going to have zeros where you're not masking. Yes, and so that what's going to give, when you multiply that by x, you're going to have the non-masked regions, okay? So you take the non-masked regions, you apply it to your encoder and your decoder, right? So that's f. So f is applied to this masked version of, well, the context version of x. Then you're going to get some output, and then you're going to compare that to your original signal, okay? So you're saying x minus the function applied to the unmasked version of x, or the context part of x, and then you're going to just want that to be small, right? So you see you have this squared loss, right? So you're just saying, I want this to be small, and then you apply the mask at the end, because basically you're saying, I only want the loss to apply to the region that I'm reconstructing, right? So basically you apply a mask over your loss such that you're only considering losses where you're reconstructing, right? So this loss is saying, I'm computing the error between what I reconstructed and what was originally there, right? Right, so, okay, I just remember what I didn't show before. So in the previous example, I kind of neglected to mention that you can kind of have sequences of encoding. So you can corrupt and then reconstruct, and then you can corrupt again and reconstruct. So you can have this stacking, right? So that was something I didn't mention before, but it's kind of okay. And so what I was just mentioning here was that in this approach, rather than have this stack, this sequence of encoding and decoding, you can simply just have like a very long network, a deep network that is, let's say, like a very complex encoder and a complex decoder. So this is just another alternative. And I would say this is very popular now to, rather than have a stack of autoencoders, of denoising autoencoders, to just simply have a very complex deep encoder and a very deep decoder as well. Right, so maybe a few more things to mention here is, so this is one way to introduce noise, right, by this mask. But of course, you can think of different ways. And the authors in this work, they considered 2 additional ones. So rather than having just a central crop in the image, they generated a few random crops, right? So they just like masked out some regions of the image. Another thing you can do is try to have a more semantic blocking. So try to map out potentially object-sized locations in the image. And so these are just sort of different ways. And once again, this is a bit ad hoc. It's just based on intuition about the types of noise that could potentially be, let's say, denoised, let's say removed. And what this work found was that actually doing something a bit more sophisticated tends to improve performance. But one thing I think is interesting to notice is that there's going to be a kind of domain gap issue, right? Because you're learning this representation. This is the encoder. And the encoder, by the way, is what you tend to use for your downstream applications, right? So when you're taking this model that has been trained this way, and you want to apply it to an actual target task, you're not going to use the decoder. You tend to throw away the decoder. You just learn the encoder. Because the encoder is what is giving you this sort of compact representation of your signal, right? But the kind of sort of issue with denoising encoders is that you train them using corrupted data, right? And that is not great for inference time, because let's imagine that you want to take this encoder and you want to use it to encode a signal, like an image for some target task, right? You want to train a classifier on a data set you collected or something like that. Then you're going to have to add noise to your image at inference time, right? And that's kind of weird, right? So why would you want to do that? Because as was mentioned before, I think David mentioned this, the assumption that's made in machine learning is that if you want to appropriately apply your model at testing time, the distribution of the data that you're applying it to should match the distribution of the training data, right? And this means that if you're training with corrupted data and you're testing or you're using it on non-corrupted data, there's a domain mismatch and it's going to affect the performance of your model. So that's kind of a limiting factor with this type of work. So this next work tries to address exactly that issue, right? So it tries to think of how can I use autoencoders without introducing some kind of corruption. And so what it does is it introduces the concept, well, what they call split brain encoders, autoencoders. This is work by Zhang et al. And the idea is to learn these 2 disjoint subnetworks, where basically you have an input signal, you decompose it somehow, and then you can consider one component to be removed. So you're in some sense adding noise, and then you want to reconstruct the other one, right? So the way they did this is they use it on image data, and they split the image into a lightness channel and a color channel. So if you folks remember, yesterday I gave the example of a colorization approach, where you had an image and you wanted to input lightness and predict color, right? So this is similar in that sense, but what's interesting here is that they take the image, they decompose it into lightness and color, and then they solve these two denoising problems, right? So you have one network that's going to have as input lightness and predict color, and you're going to have another network that's going to take as input color and then predict lightness. So when you have these two different networks, at training time, you're training one to predict the other, but then at testing time, you can use them both, right, together to give you the full signal, right? So at training time, as you see here, you have your raw data, you split it into, for example, in this one case, lightness and another color, and then it's going to give you these two outputs, right? So you can say x1 is going to predict x2, and x2 is going to predict x1. And then when you're testing, you can just combine these two models to take as input your original signal, right? So this is a really nice way, I think, of addressing the issue of this domain mismatch between training and inference. Yeah, it's kind of just what I said. Okay, so I think another work that's interesting here, also because there's a bit of a contrast with an autoregressive approach, which we won't talk too much about, but I'll just give you a flavor. So this is work that is still in the sort of autoencoding framework, right? In this case, it starts to take a flavor that might remind you a bit of transformer-based models. And so what this work does is it masks regions of the image. So first it takes an image and it kind of generates representations for, let's say, grids, like cells in the grid of an image. And then it masks some of these cells, right? So you can see here it takes an image, it kind of creates a gridified version of it, and then it stacks those cells so that you get this vectorial representation, right? And then it has kind of two ways of trying to learn a model, a representation. One is autoregressive and one is masking-based. So let's say denoising. So let's look at the second one first, B. So this is using a BERT approach. So for those, who is familiar with BERT from NLP? Okay, yeah, a good number of you. So this is the exact same, it's very analogous, right, to what was done for BERT. So you mask some of the quote-unquote tokens, where in this case tokens are, let's say, representations of a patch of an image. And then you just learn to regenerate it. Okay, so you try to predict what was masked from everything else with so-called context. And that's just what this loss function is showing you. I won't go into too much detail, but you'll see that you're saying what's the probability. You're trying to maximize the probability of the patch that you predict based on the context, right? So you kind of predict xi based on everything except xi, basically. Right, so that's the masking one. And I'm just going to briefly mention the kind of autoregressive approach just because it's, I haven't talked about this much and I won't, but it is something that you see very often, especially more in NLP maybe than in vision. And so in this case, what's done is you're simply predicting its next token prediction, right? So you are predicting your current token based on all the tokens that you've seen before, that you've predicted before. And so I'll just simply mention that both of them work quite well, but they each have their kind of own strengths and drawbacks, right? So the autoregressive objective tends to perform pretty well for generative tasks because that's what it was pretty much trained to do, right? To generate a next token based on what it has done. Objectives, so the model that was trained on BERT tends to perform really well for downstream tasks. It means that it tends to somehow generalize or transfer better to tasks like classification, detection, many other vision tasks, right? And this is an observation that was also seen in the NLP domain, suggesting that just the different objective functions tend to optimize for different things, right? So basically denoising seems to be, and this is, I don't know if there's theoretical work on this, but at least empirically, it seems to be very strong at learning rich representations that can transfer to other tasks as well. Yeah, one thing to note here is that this work, in order to address the domain gap I mentioned, the fact that you're adding noise, they actually applied noise during inference as well, which just goes to show how important that is, right? It seems kind of crazy, but what they found is that the gap between using noisy data at training time and clean data at testing time is so great that it's actually worth it to inject noise at testing time, and that improves the performance of the model. So that just goes to show how much of an issue this is. Okay, so I just have 2 more works in this line to show. So the next one is pretty recent work from Hay et al. And this work is about mass autoencoding again. So in some sense, it's pretty similar to what we just saw, right? So there are just a few differences with what I was just showing, but I think it just goes to show how, you can say, details make the difference, right? So this work is conceptually quite similar. You have an input image. You mask out some regions. You just randomly mask out some of the patches. Then you're going to throw it into an encoder. You're going to learn some representation. And then you're going to learn to reconstruct the image, okay? So what's different, basically, with respect to what I just mentioned? It sounds pretty much the same. So what they found were maybe 2, I think, important things. The first was it's important to use architectures that can scale. And then once you have that, then you can throw in a ton of data into it, right? So what they did was they proposed to use transformers, and they found a few ways to kind of have the transformer train really well. And then once you have the scalable architecture, you can throw in many, many, many different masking options, and then also mask the regions have a very aggressive masking. So basically, you're almost removing everything, right? So in this case, you can see, let's say, like a representative example of an image. I think it would be pretty hard even for us in this room to figure out exactly what this is or to reconstruct it. But you can see that it can actually do a pretty good reconstruction. I mean, actually, I think this is probably an artificial example, but I'll show you a few actual real reconstructions that are pretty impressive, right? So that was kind of like the innovation here. And another thing that was quite important is to address this domain gap up front, right? So what they did to avoid training with noisy data was to input into the encoder not a masked noisy image, but basically to just input the tokens that were not masked. So rather than input, if you have a set of tokens that, let's say, n tokens, typically you would input n tokens, but some of them would be just corrupted, right? What they did instead is if you corrupted k tokens, they just remove them, and the input to the transformer is going to be n minus k. Okay? And that means that at inference time, the tokens that are seen, there will be no corrupted tokens that are seen, right? So you never saw corrupted tokens at training, so you don't see them at test. And so from that perspective, you avoid this issue of having a different type of data during training versus testing. And I think that's pretty much it. And so just that difference, and then using the right architecture, and then also with that architecture having very aggressive scaling, masking, I should say, leads to pretty good performance. This model is one of the best performing model, at least empirically, on a variety of tasks. This is just one example to show you the kind of reconstruction that you can do, right? So this is a real example, and so the input you can see is, it's very hard for even us, right, to kind of tell what's in there, but the reconstruction that you see, and I think it's pretty cool. I was pretty surprised to see that. Yes, maybe just one last point on this, right? Like, this kind of tells you how rich these representations can be, right? The fact that from this, you can learn so much about the distribution of data that exists, that it can tell you, given this, I suspect, this is like a kind of a reasonable reconstruction. It really just tells you how rich the representations are that are being learned. Okay, and lastly, once again, this is a bit of like a kind of twist on the general idea. So far we've been looking at having signals that are images, and then adding noise to them, and then trying to reconstruct the original signal, right? So this work is a bit of a twist on that idea that instead of trying to reconstruct a signal, an input signal, you're going to try to reconstruct or really kind of predict a transformation, okay? So again, this is kind of just the comparison here illustrated, right? So typically for autoencoding, you have a signal, you corrupt it somehow, you encode it into some space, then you decode it. You decode that latent variable in order to reconstruct your original signal. That's like the standard thing we've been talking about. In this case, what they do is you have an image, you transform it somehow, using all the typical transformations we already mentioned, potentially. Then you encode both of them, the original signal and the transformed one. And then you try to decode the transformation that was done. So this is just another flavor of trying to encode these differences between the two and to represent them. So I would say this is kind of, it's described as an auto-encoding approach. I would say in some sense it's a bit similar to some of the pretext tasks we've seen before, right? By trying to corrupt something or just modify something and then trying to figure out, what was the modification that was done. Yeah, I kind of just talked through that already. Yeah, maybe one last thing to mention is this last point, which is that I think one thing that also give it an encoding flavor is the fact that it is learning a low-dimensional representation, right? So you see me and many people throw around things like encodings and embeddings and representations, and they tend to be used somewhat interchangeably, but I would say that what's kind of consistent in the, let's say, autoencoding literature and just the encoding literature, that there's a kind of expectation that an encoder is going to encode your signal into some space that is pretty compact, right? The idea is basically, once again, that you have your data lies in some lower dimensional manifold, and you want to learn a reasonable representation of that manifold. And that's it. We got to the end. So that takes us through kind of all the different paradigms, architectures, approaches for self-supervised learning. And then I'll spend just a little bit of time on the evaluation. We've kind of not talked about that at all. So I'll just spend a few slides on that. Was there a question? Yeah.
Actually, it wasn't exactly my question, but later. I wanted to ask how to evaluate the models.
Yeah, good question. Yeah, here we go. Sure.
Another question about encoder-decoder architecture. You said that we completely forget about decoder. But how can we be sure that decoder is actually less powerful, less meaningful part of our network? Maybe it is only decoder which do all the job. Is it possible that we can just use the last layer of decoder for embedding, for example?
So let me at least express why we would want to throw it away. So you can think of the decoder as, you can think of it as a bit analogous to like a prediction layer. So let's think of it this way. So like a lot of self-supervised learning methods, or let me think of it even further back, right? So very often when you want to do transfer learning, so transfer learning, just to put everybody on the same page, is when you've learned something, right? Let's imagine you train a model to predict, to classify images into different ImageNet categories, right? So you learn like a 1,000 class classifier, right? And then you say, okay, I have this model. It knows how to perform this classification task, and I don't care about that classification task anymore, right? What I want to do is I have this new application that's important to me, right? Let's imagine that I work on medical imaging, and I want to classify images into different pathologies, for example. So you're going to tell yourself, okay, I have this network that was trained for a different task, but I think that what this network has learned, what it has embedded, is going to be useful for my task, right? So I'm going to take that model that was trained on ImageNet, and I'm going to adapt it via something like fine-tuning on my target task, right? What you typically do there is you have to throw away the classifier, right? Because the ImageNet classifier is not useful for your actual task. So you take the representation, you throw away like the last few layers that represent your classifier, and then you stick on top of a new classifier, and then you train that new classifier on your new task, right? So that's one reason why you might want to throw something away, right? And this is pretty similar from that perspective. So the decoder is being used being used as part of a task that allows you to learn a good representation, but then when you have your target task, you kind of don't care about it anymore. And so that's kind of just a justification for why you might want to do that. Now, could it be that somewhere in the decoder, there might be an output, like an intermediate output that's useful? Quite possibly. It just tends to be the case that people are very interested in having this compact representation, and that's where that's how the decoder tends to be learned. And so, especially for images, as you go from this latent representation and you kind of progress it through the decoder, the representation tends to be less and less redundant. It tends to be less and less compact, because what you're trying to do is reconstruct the input signal, right? So typically, the encoder, the embedding out of the encoder is going to be the most compact representation you have. So that's kind of one reason also why it's more attractive to use that than an actual decoder layer output. Okay, so yes, evaluations, very important.
Yeah. Well, more questions.
Okay. Thank you. My question is related to the policy distillation in the contrastive learning. So I'm merely curious that most of the time, even in the literature, we have seen policy distillation. Whenever people are applying policy distillation, they are using with the teacher and the student the softmax as an activation function. But imagine if we are trying to implement similar concept but with something like a regression problem. We cannot exactly use softmax. So do you think the softmax itself is playing some sort of a role with the policy distillation, or it can be used with some other activation as well, like mean squared error in case of a regression problem, and it should still work?
Yes, I'm not super familiar with policy distillation. Is this in RL context? Maybe I'll answer like a bit more generally. So why is softmax important? So one, I would say that it's, for me personally, the concept of distillation does not necessarily rely on softmax, right? The idea of distillation for me is really having a teacher that has some embedded knowledge and having a student that you want to kind of distill the knowledge from, especially if the student is smaller, because then there's this concept of kind of distilling the knowledge from the teacher. That, for me, that's like the essence of distillation. However, I think probably the most influential paper to talk about distillation did include softmax. So what they did was they did use softmax, but they used a tempered version of softmax. So they used this temperature parameter, which I don't know if you're familiar with. So basically, I probably have it somewhere, but I don't want to go through the slide, so I'll try to describe it. So when you have softmax, you have some similarity measure, right, that you exponentiate, right, and then you have a normalization at the bottom. So this normally gives you a very peaky distribution, right? So if you're looking at this distribution, the distribution will normally be peaky, right, where there's a highest similarity, highest probability. So what you can do to make the distribution a bit more flat, right, so to basically kind of push down the peak and make it just a bit more evenly distributed, is to include this temperature parameter, which you can say is already included, but it's just 1, right? So it doesn't really do anything. But then if you make the temperature very high, then you make the distribution very less peaky, right? And if you have a really high parameter, then your distribution goes from being like a peak at the most likely position in the distribution to being flat, right? So you can think of this temperature as a parameter that goes from making your distribution peaky to making it very flat, right? Making it equally probable across all the possibilities. And so that's one reason why I would say softmax combined with a temperature parameter can be quite useful. Why? Because if you have a distribution, if you have your distribution from your teacher, then you have your distribution from your student, and you want them to match, if the teacher distribution is very peaky, then your problem is going to be almost like a classification problem, right? You're basically almost at the point where you're saying, I want my student to predict exactly the same category as the teacher, right? And what a temperature gives you is it's in the paper they kind of describe it as sort of like hidden knowledge, which is kind of telling you not just that the teacher thinks that this image input is most likely to be a cat, for example. It's also saying that it's most likely to be a cat, but maybe it could be the dog, but maybe it could also be a horse, because you also start to have some non-negligible probabilities for other classes, right? So I wish I had a thing to draw. So basically, if you have, let's say you have 5 classes, right, and you you have a very peaky distribution on dog, then you're gonna, all that information will simply tell you, this is very likely to be a dog, but you don't get a lot of information about what else could it be, right? If you make that distribution less picky and you start to have non-negligible probabilities for a dog or for cat, then you get additional information. So you're not just learning that this is most likely to be a dog, but you're learning it's probably not a horse, that's super low, but it could be a cat because it's a somewhat high probability, etc. So that's what a kind of softmax can give you, sort of extra information. So I would say that's kind of one reason why this is very used. That being said, it is true that if you have a model that was not trained for classification, let's say you have a teacher that was trained for a regression task, and you want to apply that model to some other task, then you're basically not going to be able to do a softmax, right? So you have to think of some other way to do it. And I'm pretty sure there are works that exist for it, but it just means that you're not going to have this, so they're not going to have this temperature parameter to play around with. So yeah, so. Mm-hmm.
So can the student and the teacher have access to the same training environment, or they have a different sort of a training access to the different observations from the training environment?
No, so typically they would have the same. If by training environment you mean training data, for example, and labels, yeah, they tend to have the same. So they tend to be smaller. So the student in the, I guess you would say the most.
Could you repeat the question, please?
So my question was basically that if the training environment in which we train the teacher network and in which we train the student network, whether both of them have the access to the same network, or for example, the teacher network could have access to a more detailed environment with a lot of more observations, as opposed to the student who is being trained in a very compact environment with limited number of observations only. Because if we do the exact same environment for both of them, then why is there a student or a teacher network?
Well, you definitely sound like somebody who works on reinforcement learning. So typically what's different is that you have a teacher that is, canonically, the teacher is just a bigger model, right? So that's like a key difference. If the environment is the same, but the model itself, like for example, there are much fewer parameters, and that's going to be an important difference. It is true, though, that some distillation paradigms do have exactly the same teacher architecture, and in that case, indeed, the information may not always be the same, right? So sometimes, for example, the student only has access to the output of the teacher. So whereas the teacher might have actual labels, the student only has the output of the teacher. So that's another kind of instantiation of the problem.
Good. Thank you. One more question.
Hello, sorry. Just a quick question. I've seen recently some training loss based on mutual information between input and output. So how would you compare it to other approaches for contrastive learning? Thanks.
Great question. So I didn't touch on that at all. There's a lot to cover in self-supervised learning, and so that's yet another strain of it. So there's been some work that has contrasted this, I think, even on a theoretical basis. So what you can think of is, so for mutual information, right, if you deconstruct what that is, right, like computing the mutual information between two different sets of signals, there's going to be a component of that mutual information loss, right, or mutual information, let's say, not loss but objective, right, where some part of it is trying to say that you want if you want to maximize mutual information between different views, right, that kind of breaks down into trying to have the views be, let's say, I don't remember the exact breakdown of it in terms of the formulation of it, but it's, let's say, I think there's a way to derive a lot of the contrastive learning approaches we've seen from a mutual information objective. So honestly, I think it's very much a variation on the theme of contrastive learning, and I think there have been a paper or two out that actually did a theoretical comparison, like a formulation comparison between mutual information, break it down into different component terms, and then compare that to some contrastive learning approaches, and you will see that it actually kind of breaks down into some contrastive learning approaches and some sort of similarity-based approaches as well. So yeah, good question.
Yeah, I think with that, let us thank Naila, and she has another talk tomorrow, and then we'll break for lunch. So thank you very much.
So I did want to cover evaluation, but I see we're out of time. So what we can do, we can either take 5 more minutes if it's okay. Okay, sorry about that.
I thought we were in question.
No, yeah, I know, we had a lot of questions, so no problem. So yeah, I know everybody's hungry, but I figure rather than like drag this on even further, let's finish this, and then then I'll let you guys go, I promise. Okay, so evaluation. It's not that many slides. I think we'll get it done in 5 minutes or so. So yeah, I've been spending 2 hours talking about self-supervised learning, right? And learning these representations, these very rich representations, and let's keep in mind what this is all for. The reason why this is super interesting is because we can take these representations that we hope are very, let's say, how should I say, polyvalent, right? That they can be used for lots of things, and then apply them for a lot of quote-unquote downstream tasks or target tasks, right? So I gave an example just now of saying, I have an image that was trained on ImageNet, and if I personally want to train a model for a different task, like classifying different medical images, then this would be considered my target task, right? And I want to think of how can I transfer it, right? And so this is exactly how these models are evaluated. Basically, you take a basket of tasks, you try to say, okay, a good representation should be able to transfer well to classification tasks, a variety of different classification tasks, maybe some object detection tasks, maybe some semantic segmentation tasks, other tasks as well, right? So you just basically collect a lot of these different tasks and you try to evaluate the model's performance on those tasks, right? But not quite, there are some details which I'll get into. So here, just in case like you're not familiar with some typical computer vision tasks, I think you've seen some before in David's talk, but just to remind you, so types of tasks you might be interested in are things like object detection, where you have this image, you have this jackal in the image, you have a car somewhere there, and you want to be able to say, there is a jackal in the image and it's located here, there's a car, it's located there. That's one typical task of interest. And you can think of this as very useful, for example, for autonomous driving or for driving assistance, where you want to be able to, the system might need to do this, right? It will need to do this. Another example is image segmentation, where you have an image and you want to label every pixel in the image with some category, right? So this region corresponds to road, etc. Once again, also very useful for autonomous driving. Another also actually useful for autonomous driving is depth estimation, where you want to say for every pixel, I want to predict the distance to the camera, right, from the object that reflected that color, right? So these are all different examples of tasks we might want to do, right? And so what we're going to do is we're going to evaluate how the model transfers to that task. Right, so the first one is probably most typical one is some variety of image classification. So what's typically done is, I would say probably the one you will find in probably all of these types of papers is some kind of probing on ImageNet. So when you see the term linear probing, what that corresponds to is just simply taking the representation that you learned, freezing it, meaning like not updating the weights anymore. The weights are fixed at this point. Then what you do is you introduce a new layer, which is some sort of classification layer, typically like an MLP, and you learn that layer only, right? So because this linear, if you just jump to the last bullet point there, so because you're only going to rely on this linear layer for your fine-tuning, right, the representation itself ought to be pretty rich, right? Because if all you have is this linear layer, and you're going to use this to classify some downstream task, to apply to some downstream task, then if the model performs well in this scenario, it's a kind of indication of how good your representation is, okay? So what I'm showing here is well, actually, maybe that's not super meaningful yet, so I'll describe the actual fine-tuning process. So I've talked about the term fine-tuning a lot. I hope you're all familiar with it. If not, I'll just say that fine-tuning is simply taking some weights that have been trained on some task and then updating them even further, right? So that's why they're called fine-tuning. You have some initialization that's useful, and then you want to kind of improve upon it via this process we call fine-tuning. So it just means like training it additionally and typically on a different task, okay? So this, I'm just showing you some results from the masked autoencoding paper I showed earlier. So I mentioned this work that, that basically learns to reconstruct some missing pixels, missing patches, and it's the one that does a very aggressive masking, right? So this is just some recent work. And so what this is showing, forget the text, I'll just describe this. So what this is showing is that if you take a model, you train it from scratch to perform ImageNet classification, okay? You get some performance, so in this case it's 82.5%, I think, top 5 accuracy, I think. And then what this is showing, this MAE result, is showing that if you take a model that was trained first using masked autoencoding, so without using any labels, and then you fine-tune it on the task of ImageNet prediction, you get a better result than you would training by scratch, right? So what this is telling you is that basically it's the same process, just in one case, you've done this pre-training step using masked autoencoding, right? And you see you get like better performance. It may not look like much, but this is pretty meaningful, right, for an ImageNet classification task. And so it just tells you the power of having powerful initial representations to improve some task you're interested in, right? So it's just simply saying there's always, once you have some supervision material, right? So if you have an annotated data set, you can always train from scratch. But what you will definitely see is that having an initialization that's good is going to dramatically improve your performance in many cases, especially if you have a limited training set. And actually, like my last talk tomorrow, we'll talk about that some more. So I just mentioned image classification as one sort of evaluation task. I'll just simply mention briefly that typically for a robust evaluation, you're not just going to want to evaluate on one problem, right? You want to evaluate on many problems. And so you typically evaluate on multiple different classification tasks, right? So this is just showing a few more. And also, folks typically, for vision representations, you typically also evaluate on some object detection or some image segmentation benchmarks as well, right? So I hope that's clear. That's typically how these things are evaluated. It's very straightforward. It's basically just saying the idea is that it works well if you fine-tune it on a new task. And so you collect a set of tasks, and you just fine-tune the model, and you say, okay, does it perform better than not using this pre-trained model, okay? So hopefully that's clear. I'll let you folks go now. And if there are more questions, feel free to ask me now or tomorrow.